Hi. So I'm still home. I'm still not feeling too great, but I feel much better. And I decided to try to record Lab Lecture 3 and to try to make it on the short side so that it doesn't, take forever for you to watch it because I don't want to do that. But anyway, so what the reason I'm giving this class, I never used to give a Lab Lecture 3, but but in P Chem Lab, we use a lot of equations that we don't actually derive in physical chemistry until the end of the semester. So a lot of the knowledge I'm asking you to use to answer questions and stuff like that comes from stuff you learned in Chem 104. And how much you absorbed back in Chem 104 is really, I don't know. It depends on who you had for a teacher, depends on where you took the class, depends on how much you paid attention. So I just want to go over some of these fundamental equations that you're going to need to understand in order to answer questions and in order to, in some ways, understand the calculations as well. Okay, so the first thing is from the second law. And I did mention this the first day of class, but I also told you didn't have to really know everything I said the first day. So the second law basically says that for a spontaneous process, and a spontaneous process is a process that happens on its own. So for a spontaneous process, that total entropy increases. And yes, you can think about entropy as disorder, but total entropy means something specific, which I'm going to go over with you in a minute. So total entropy increases, but chemists often think about this in terms of the Gibbs free energy G. Gibbs free energy decreases. Okay, so that means that this S total, S is the symbol we use for entropy. S total is the total entropy. S total must increase for the spontaneous process. So the change in entropy, the total change in entropy, must be positive. And that the delta G, the change in the Gibbs free energy, must be negative. These are the conditions, or they're actually one and the same condition, really, which I'll tell you in a minute. But this is what must be true if a reaction or a process is spontaneous. Now, delta S total actually consists of two parts. There is the change in entropy to the system, which we never use a subscript when we're talking about systems. So I'm not going to put a system subscript there. You have to know that the delta S without any subscript refers to the system. And that the other part is the change in entropy to the surroundings. It's funny, I start recording and I immediately get all these problems with the pen that I used to get when I did all my recordings. So let's first look at it from the point of view of the delta S total. All right, so I mean, I'll get back to this part about delta G, but what I want us to think about now is, when does system entropy increase? In other words, what type of processes? And then the answer to that would be there's a few different situations, which I know if I taught you Chem 104, we go over this in class. I have a handout on it and everything. So system entropy, which you could think about as system disorder, increases for certain types of processes. So for example, if you have a solid going to a liquid, that is going to have a positive change in entropy to the system. Why? Because a liquid is way more disordered than a solid. it's moving, molecules are moving around a lot more. Solid is very rigid, very ordered. Okay, so solid going to a liquid, let me write SOL for solid, will have a positive delta S generally. A liquid going to a gas, also definitely a positive delta S, because gas molecules are moving. Liquid molecules sort of moving a little bit, but they're not moving as much as gas molecules at all. I'll put another one in here that if you're going from, say, solid to aqueous, that's usually, that's a positive delta S. Because again, you're going from a very rigid solid to ions that are allowed to move around, or dissolved particles that are allowed to move around, depending on whether you have an ionic compound or not. Another rule of thumb that we use is system entropy increases when the number of moles of gas increases. So if you have a reaction where you have, you know, 1 mole of gas on the left and 2 or 3 on the right, you almost certainly will have a positive change in entropy, because like I said, gas molecules have all that movement and the most disorder of any form of matter. There's another rule of thumb is if you go from like more complex, say a more complex molecule, let's say, this pen is not writing very well, sorry to say. Why? It's really bizarre. One more complex molecule goes to, say, 2 or more less complex molecules. Okay, so you're decreasing numbers, then this will generally have a positive delta S as well. Basically, one molecule versus two molecules will have a greater amount of disorder. You know, one molecule can move around, but 2 molecules are going to move twice as much. So basically, that would also give you a positive delta S. So those are kind of the reasons why system entropy might increase. Okay, so remember, that's one of the 2 parts here, that the change in the total entropy is the sum of the delta S for the system. And now I want to consider, what does delta S surroundings depend on? And for the surroundings, it's really a very different consideration. And we can really determine very easily what the sign of the delta S surroundings is, as long as we know whether the reaction is exothermic or endothermic. So here is the basic idea. You have your system. You can consider this box to be the system. Okay, if heat leaves the system, okay, there's only one place that it could go. If heat leaves the system, it goes into the surroundings. It heats up the surroundings. What does that do to the order of the surroundings? Well, when you dump a bunch of heat in something, the molecules move a lot more, okay? Heats up surroundings. This increases the disorder of the surroundings. So delta S surroundings will be positive, and that's what's true. This is for an exothermic reaction. So for exothermic reactions, delta S surroundings is positive. Not only that, but the delta S surrounding in general is the we will learn about this in class. It's actually the negative of the delta H divided by the temperature. So you could see that if delta H is positive, if delta H0 is negative, which is the example I'm giving you here, then delta S surroundings will be positive. On the other hand, if you have this situation where the heat flows into the system from the surroundings, so I'm talking about an endothermic reaction with delta H0, waiting for it to catch up. Which delta H0 negative. Okay, then that's taking heat away from the surroundings. That's actually making the surroundings more disordered. Sorry, more ordered, duh. More ordered. Just like, well, you probably don't remember, but that's okay. So if delta H is, oh God, delta H is positive. Sorry, folks, let me just do this again. If heat flows into the system from the surroundings, it's endothermic, delta H is positive. This makes the surroundings more ordered. So if you had, say, a gas moving, fast, and you took some of the heat from that system and moved it into, from that surroundings and moved it into the system, the gas molecules would be moving more slowly. Or maybe a liquid would become a solid, like in the example I did the first day of class. But anyway, if delta H0 is positive, then delta S surroundings is negative. So you can always tell what the sign of delta S surroundings is just from the sign of the delta H. How do you tell what the sign of delta S is? Well, for that, you look for these different rules of thumb: phase changes, moles of gas, complexity of the molecules, and how many molecules you have. Okay, so those are good things to look for. So let's see. So for spontaneity, just again, we had delta S total, which is the sum of these two contributions, must be greater than 0, or delta G must be negative. I'm being a little sloppy about the notation here. I didn't say anything about standard conditions or anything like that, but in P Chem, we actually would say that delta G zero, let's just call it delta G for now. Okay. So in P Chem, we actually use this expression for delta G0. This is the change in the Gibbs free energy under standard conditions. And we say that it's equal to delta H minus T delta S. There's actually a hidden condition in this equation, and the hidden condition is this has to be at a constant temperature, which we'll learn about later. But anyway, we have this relationship here, and I want to show you that this business about, either of these two things, delta G being negative or delta S total being positive, that these actually are really exactly the same thing. That if I actually take the negative of this equation, so I multiply by -1 and I divide by the temperature, so I end up with negative delta G0 over T equals negative delta H over T plus delta S. The T's cancel. And you could see that this sort of lines up with this is the same. And I said that the delta S, sir, is the negative of delta H over T, which unfortunately is something that we learn a lot about, but we haven't gotten there yet in the course. But you could see that, that there's that, since I've already said these are equal, that these two guys must be equal. So if delta S total is positive, delta G0 must be negative. And so these are really equivalent relations. Okay, so it doesn't come from nowhere that delta G has to be negative for a spontaneous reaction. We spend a lot of time on this. We spend a lot of time on this equality here. Unfortunately, we can't do that right instantly at the beginning of the semester. All right, so I already talked about why delta S might be positive or negative for a given reaction. I'd like to talk a little bit about when is delta H positive or negative. And so what this really has to do mainly with is the bonding situation. So if delta H is negative, it means that the products are more stable than the reactants. That means that the products either have more bonds between them, between the atoms, than the reactants did, or maybe they have stronger bonds. Okay, so I would describe this as the products have more or stronger bonds between their atoms. Than the reactants. Okay. More and or stronger bonds. That's one way of having that. There might be a situation where you have the products there are stronger intermolecular, everything else is equal, let's say, for reactants and products, but maybe the products have stronger intermolecular forces with the solvent than the reactants did. Okay, that's kind of what you're looking for. Products could have stronger intermolecular forces with solvent than reactants. Can you think of an example where that might be true? Like if you had an aqueous solution and you had neutral molecules that suddenly became charged at the end of the reaction, those charged particles might interact more strongly with the solvent, and that would stabilize the product. So products can have stronger intermolecular forces with the solvent than reactants. Now, I guess I could also have said products have more attractions between them than reactants, because sometimes you don't actually form a bond in a reaction, you just have a stabilizing attraction. So I could say products have more, I'm just sort of being very vague about what I mean by attractions, than reactants, because some things are not bonding attractions, they're just maybe electrostatic attractions or something like that. All right, so those are, so when I ask, you to say, well, why does this reaction have a negative delta H? The answer is not because it's exothermic, because that's really saying the same thing. A reaction has a negative delta H is equivalent to saying it's exothermic. It's equivalent to saying it's giving off heat. So giving me an answer like delta H is negative because the reaction gives off heat. Well, sure, you could say that as long as you also tell me why it would give off heat. It gives off heat because there's a more stabilizing interaction between blah and the products than there was in the reactants, or, must be more or stronger bonds have formed than in the products and in the reactants. You need to give me something with a little more meat than just because heat was released. Okay, so all right, so I've talked about delta S and delta H. I talked a little about spontaneity. I want to get back now to delta G because this does come up in the lab, and I do ask you for things like this, for some explanations involving delta G. So here's that equation. And I just want to reiterate, and I know I teach this plenty in Chem 104 at the end of the semester when everyone's really tired. And I would say the sign of delta G depends on the signs of delta H and delta S. And also all these little zeros here mean that I'm really talking all the time about standard conditions. I'll talk a lot more about that in the class. So if you just say under standard conditions, you're covered here. 273 Kelvin, 1 atmosphere pressure, all gases, 1 molar, all solutions. So it's not that critical that you know what that means right now, but in the future it will be. So talking about the signs of delta H and delta S, we have 4 different situations that are possible. Okay, we could have delta H being positive or negative, and we could have delta S being positive or negative. So for example, if they're both, if one is positive, like delta H is positive and delta S is negative, or we could have they're both positive, or we could have negative positive or negative negative. So these are the 4 possibilities. Okay, and there's only 4 possibilities. Now, if delta G is delta H minus T delta S, so let's look at that. So let's consider the sign here. Give myself a little more room. Didn't work. This thing is not behaving very well today. Oh, well. Anyway, so delta H is positive. Delta S is negative. So that means minus T delta S will be positive. I really do need some extra space in here. Whoa, it's really freaking me out here. Just put this in later. Okay, so that means that both terms in delta G0 really, are positive. And so, it would have to be negative to be spontaneous. So that would mean that this reaction is non-spontaneous. Okay. There's nothing you can do about it. Under standard conditions, it's not spontaneous. All right, let's look at the next example, which was positive, positive. So here we have delta G is delta H minus T delta S. And looking at the signs, again, we have positive, but now we have a positive for delta S. And now we have what I would call 2 competing terms. Okay, so what this tells you is that if the magnitude of the T delta S term is greater, then this negative contributing term will dominate and the reaction will be spontaneous. Okay, when will that happen? That's going to happen when the temperature is high. Okay, so this is where back in 104 you were able to say whether the reaction would be spontaneous at a high or low temperature. I'm not even sure you're ever asked that in P Chem, but you might be asked, which of the terms is dominant, and whether you can, if you know the values of delta S and delta H, you could figure that out based on what the temperature is. So there's 2 competing terms, and spontaneity depends on the temperature. There we go. Going back to our next situation, if we have negative, positive, okay, then we have delta G is delta H minus T delta S. Okay, we have negative, positive. So this term here will be negative. Now we have two negative terms, both would contribute to a negative delta G0. This will be spontaneous, okay, because delta G will be negative. And finally, if we have both negative, okay, then we'll have delta G is delta H minus T delta S. We have negative, negative. This will be positive. Again, we have two competing terms. And it depends on whether the magnitude of the T delta S or the delta H is greater. So the spontaneity depends on temperature. And of course, if this term were a greater magnitude, the positive would dominate. It would be non-spontaneous. That would be at a higher temperature. So this would be non-spontaneous at a higher temperature. All right, anyway, and spontaneous at lower temperatures. So, so I also want to say that we can use this formula here, this equation. If you're given, if you know any two of these, you can find the third. Indeed, in the I think it's a charge. No, in the I think it was in problem 3. You knew delta G, yeah, and you know delta H, and so you actually can figure out the delta S. Then a lot of times we just change the order here and change the sign. So I multiplied through by -1 or -1 basically. And that's the formula for a delta S. And so, you know, that is used in some, I think it's used in at least one lab. And then there's the equation, which is very important, which is derived at the end of the semester, that relates the change in the Gibbs free energy under standard conditions to the log of the equilibrium constant. So this is a really very important equation, and it's used in labs, and it's derived, like I said, late in the semester. So what I ask of you here is that you make some mention of whether the value of K is consistent with the value of delta G. So you need to consider the consistency of your results. I'm not talking about if you make mashed potatoes, what their consistency is. I'm talking about whether it's consistent that K and delta G have whatever values that you got. So what do I mean by that? Well, so if K is greater than 1, all right, so it's a big number, let's say, this would mean, what does that mean? Well, remember that if you have reactants going to products, you have an equilibrium. At equilibrium, the K at equilibrium, which I'm trying to write, but I'm not able to, at equilibrium, K is the concentration of products over the concentration of reactants. If it's gas pressures, if it's gases, and it's pressures, but whatever. So, a larger K means that products are favored. And so that's what I mean when I say with K greater than 1. That's favoring the products. Now, so if K is greater than 1, products are favored. this would be consistent with what sign of the delta G zero? If K is greater than 1, products are favored. It's consistent with a negative delta G zero, because a negative delta G zero means the reaction is spontaneous in the forward direction under standard conditions. So, how would you ever make more products if the reaction wasn't spontaneous in the forward direction? So a negative delta G zero is consistent with a K value greater than 1. Of course, you could have K values that are 1.01, and you can have K value that's 10,000, okay? The more greater than 1, the more greater than 1 K is, the more negative delta G zero is. Okay, so if you get a value of K that's 0.01 or something like that, and then you get a negative delta G zero, there's something wrong. You did something wrong there. That's not consistent. So what I want you to do is make sure that you get consistent answers, and this can help you check your answers as well. Of course, I didn't say it, but it goes almost without saying that if K is less than 1, then delta G zero must be positive, okay? And the smaller the K is, the more positive the delta G zero will be, okay? So that shouldn't be a big surprise to you. Okay, so there's another equation that we use a lot in P Chem Lab, and this equation, there's many different forms of it. It's called the Gibbs-Helmholtz equation. And it actually relates changes in the equilibrium constant of a reaction with changes in temperature. So it has to do with how equilibrium constants, how K changes with temperature. Does it increase with temperature? Does it decrease with temperature? And this depends on the value of the change in enthalpy of the delta H. So what I first want to do before I tell you what this equation is, and you've actually used it, you used it in problem 3, so it's not going to be a big mystery, but I want to first talk about how K should change with temperature when a reaction is exo versus endothermic. So that's the first question. How should K change with temperature for an exothermic and an endothermic reaction? So let's go back to Gen Chem. And let's first consider endothermic reactions. An endothermic reaction you could think about as adding heat to the reactants side. So you have reactants, you add heat and form products. Now, let's use Le Chatelier's principle. So if you add heat, you heat this up, so you increase the temperature, stress of adding heat because of a temperature increase. If you add heat, what is that going to do? The system is going to respond in such a way that removes the stress, so the reaction will go to the right. Okay, when it does, now you're favoring products more. So the K goes up as the temperature goes up. That's for an endothermic reaction. So for endothermic reaction, you have a greater K at a greater T. The opposite is true for an exothermic reaction. Well, exothermic reaction, the heat is on the product side because heat is released. So reaction goes to products plus heat. So now if you increase the temperature, so you add heat, it's like adding a product, and the reaction goes in the reverse direction. So for an exothermic reaction, increasing T leads to less product, less product, a smaller K value. So it's the opposite. K goes down as T goes up. Okay, that's what happens for an exothermic reaction. Okay, so that's what should happen. So now I'm going to give you one form of the Gibbs-Helmholtz equation. Lots of different forms of this equation, and we use a few of them in P Chem Lab. But what I will call the differential form, it's basically how the log of K changes with temperature. And seeing as we're able to make conclusions only if we know the sign of the delta H, it stands to reason that the change in the log of K, or the change in K with temperature, here it's the change in log of K that we actually will know from this equation, it depends on the delta H value. It's equal to delta H0, it turns out, over RT squared. So what does that mean? Okay, is that consistent? This is the differential form of the Gibbs-Helmholtz equation. Okay, so what we don't, if we were able to plot the log of K versus temperature for an endothermic reaction. Okay, so for an endothermic reaction, delta H is positive. So that, temperature can never be negative, R is positive. So if the reaction is endothermic and the slope of the log of K versus T should be positive. So it should look something like this. They should have a positive slope. So that means as the temperature goes up, right, we're going this direction, the log of K should go up, so K should go up. Is that what we said here? As temperature goes up, K goes up for an endothermic reaction. So that works. And of course, the other thing is going to work as well. If we have an exothermic reaction, okay, the only thing that can have a negative sign here is the delta H. If delta H is negative, the change in the log of K with respect to T, the slope of a graph like this would be negative. So as the temperature goes up, we're going now this way, we're going downhill. Okay, as temperature goes up, K goes down. Okay, so as temperature goes up, K goes down for an exothermic reaction. We are favoring the reactants more at the higher temperature for an exothermic reaction. So you might not know where this equation comes from, but at least now you know that it is consistent with what we know from Le Chatelier's principle. Okay, now, like I said, there's different versions of the Gibbs-Helmholtz equation. What do you do with an equation like this when you have a differential form? Oftentimes, you'll integrate it. And there are a couple of different integrated forms of this equation. The one I'm going to give you is when you do a definite integral. So this is an integrated form of the Gibbs-Helmholtz equation. And that is the one you used in the problem 3. I think it's also used in the charge transfer lab. Actually, to show you where this comes from, if you wanted to integrate this, you'd have d log k equals delta H0 delta H0 over RT squared dt, moving the dt to the right. So you'd integrate this. So you'd end up with log of K2 minus log of K1 on the left, which is log of K2 over K1. And then here you would have to say that delta H is independent of temperature. And then you're basically integrating 1 over T squared times dt, which gives you 1 over, it's like a negative 1 over T2 minus negative 1 over T1, which then you could make T1 minus T2. It comes out to this when you finish the integration. But this is really just, this equation just comes from integrating this between two limits. Anyway, okay, so I want to talk about how to handle this equation and how to think about it, because what you want to be able to do is use, first of all, a lot of times you use this equation to get the delta H. So you'd have to solve it for delta H0. And you don't want to make a mistake with a sign here, okay? Because we know, well, I've just talked about it, that if delta H0 is positive, then the K goes up with increasing temperature, then K increases with temperature. So that means, what is K2 and K1? I should explain that K2 is K at T2. K1 is K at T1. So if delta H is positive, then K increases with temperature. So so K2 must be greater than K1, right? So let's look at this. What I do, I've been doing this a long time, so I highly recommend this, is I always make T2 the higher temperature. That way, this difference here is always positive, and this whole factor here is positive because temperatures are positive. We have to use kelvins, right? So if that term is positive, okay, and if delta H is positive, then the log of K2 over K1 has to be positive. So if T2 minus T1 is positive and delta H0 is positive, then the whole right side is positive, okay? That means the log of K2 over K1 must be positive, and that must mean K2 is greater than K1, because only the log of a number greater than 1 is positive. If this ratio were less than 1, then the log would be negative. So what I always do is I always make T2 greater than K1 and then T1. I make sure, that I plug in for K2, K at the higher temperature, and K1, K at the lower temperature. If delta H is positive, I'll have K2 will end up being the larger number. But if delta H is negative, it'll be the opposite. Okay, so you just have to make sure that you have consistency. Anyway, that's kind of what I wanted to say there. In the Chemo Chipson lab, you actually use the differential form. This is in the second rotation, but I discussed this in the PowerPoint, so I'm not going to need to talk about it here. I want to go back to one little thing I said, because I don't want you to get a wrong impression here. And the thing that I want to go back to just for a couple of minutes is if you have reactants plus heat goes to products. And I said, if you increase the temperature, you add a stress, right? You're adding heat. It'll drive the reaction this way, and you'll have greater value of K at equilibrium. I want to emphasize that it's only for changes in temperature that you will change the equilibrium constant. If you have reactants goes to products and you add reactants, that will drive the reaction towards the products, but you will have the same equilibrium constant. When the new equilibrium is reached, it will have the same value of the K. You've just altered the quantity R, so you have to alter the quantity P accordingly, but K will be the same. So when an equilibrium is disturbed by adding or taking away reactants or products, so when an equilibrium is disturbed by adding or removing reactants or products, K stays the same. You will generate more products in this situation, but the K is the same. When the temperature changes, K changes. So it's very special, these temperature changes and their effect on the equilibrium constant. Okay, there was one more thing I wanted to go over a little bit. I talked about the meaning and the signs of delta H, delta G, delta S. There are some what I would call exceptional cases involving the sign of delta S for a reaction. So, and one of them one of them we have a lab where we have micelle formation. Okay, so when you form micelles, you have these monomers. Okay, they aggregate and they form, something. Not to have forever to draw this, but you've seen these things before. Just waiting for the old pen. It's terrible drawing here, but so here you have a micelle. Here you have monomers. And so this is an aggregation. So you would think, what would you think about the sign of delta S? Well, as far as these monomers are concerned, these detergent molecules, they do become more ordered here. So the detergent, the C-tab, the molecules get more ordered. But it turns out that delta S is actually positive. Okay, so if the detergent molecules are getting more ordered, you would expect that the delta S would be negative. But in fact, the delta S is positive. So why is that? Well, here's one of these cases where you got these long chains. And the thing is that you have all these water molecules trying to get away from these, long hydrocarbon tails. And so what you're doing is you're massively affecting the order of the water molecules here, okay? So water molecules are actually freer to move on this side. So H2O molecules are more restricted when they're surrounding monomers when they surround more compact micelles. Okay, and so sometimes the solvent makes a big difference. So the delta S0, the total, this is still system entropy. The system entropy has two contributions here. Delta S for the molecules and delta S for the solvent, which is the water. And in this process, while the delta S for the molecules is negative, for the solvent, it's positive. And this actually, for C-tab, this is the dominant contribution. This is also relevant in protein folding. And I have a little something written on that in the chymotrypsinogen lab, which is in the second rotation of labs. Okay, so it turns out that if you're going from, say, folded, which is a native, to unfolded, denatured, that the protein itself, right, the delta S for the protein is positive, okay, as expected. But the water molecules are less ordered around the folded protein. So delta S water is negative, okay? And the delta S is the sum of the two contributions. Okay, so this can be positive or negative, this total, depending on which protein we're talking about, or which micelle system in the other case. But anyway, all right, so that's really all I have to say for lab lecture 3. If this is recorded right, I'll post it. And I'm hoping to see you guys Wednesday.